Okay, so here's the Zoom meeting this week for Physics 231C. We're finishing the third week of the semester right here. We're working on chapter 3. The reading quiz is due tonight. Most people have already done it. And then the problem set is due next Monday. Then there'll be one more chapter, chapter 4, in the last week of January and the first few days of February. And then we'll have exam 1. Chapter 3 is called Motion in Two Dimensions. And there are a number of problems which involve motion in 2 dimensions, but two of the most important are projectile motion and uniform circular motion. Projectile motion is simpler. Uniform circular motion we'll be using throughout the rest of the semester. So this chapter 3, most of the homework problems will deal with either projectiles or uniform circular motion. Now, as you read the chapter, you should take notes. And then use those notes when you do the homework. The notes will mainly be equations. And you'll need those equations to solve the problems. You should have about 1 page of notes for each chapter, front and back. So you should have a notebook for physics, and then on 1 page, take notes as you read the chapter. You'll need those notes when you do exam 1. In exam 1, you're allowed to use 1 page of notes, again, front and back, which you prepare yourself. And you should take those notes out of the notes that you've been keeping while you're reading the textbook. So to prepare yourself for exam 1, you'll want to collect the notes from chapters 2, 3, and 4. If you've already got them, it'll just make it a lot easier to get yourself ready for the exam. All right, so let's go over some examples to see how you can do problems involving motion in 2 dimensions. Start with this one, the geosynchronous satellite. So this is a problem in the homework assignment, which is due Monday. There are many geosynchronous satellites in orbit around the Earth, which are used for various purposes, like weather satellites and GPS system. A geosynchronous satellite revolves around the Earth on a circular orbit. In this problem, the orbit radius is given. So this radius, r, is 6.63 times the radius of the Earth. So this is more or less drawn to scale. The period of revolution of the satellite is 24 hours. So as the Earth rotates around its axis once every 24 hours, the satellite goes around the Earth in the same amount of time, once every 24 hours. So that means the satellite is always directly overhead for some point on the Earth's surface. the radius of the Earth is a number that you're going to need in this problem. So that's 6.371 times 10 to the 6th meters. 6,371 kilometers, or about 6 million meters. Now the question is, what's the acceleration of the satellite? The satellite moves with a constant speed. But since it's moving in a circle, its velocity vector is constantly changing. This would be the velocity vector when it's at this point, tangent to the orbit. But when it's over here, when it's at this point, its velocity vector will be in this direction. Always tangent to the orbit. So always tangent to the circle. So you can see how the velocity vector has changed from here to here. The length of the vector should be the same. So it's constant speed. Speed is the magnitude of the vector, but the direction is changing. A change in the velocity vector is an acceleration. So at every point along the circle, there's an acceleration, and its direction is directed towards the Earth. So it's constantly being pulled back towards the Earth. Of course, the reason for that acceleration is gravity, but we're not talking about gravity today. We're just talking about the acceleration vector. That acceleration vector is called centripetal acceleration. So you should have the equations for centripetal acceleration in your notebook. All right, now here's how to do a physics problem. Step one, draw a picture and label the variables. Now in this problem, you already have a picture, but you should draw your own picture in your notebook. Step two, write down the relevant equations, not putting in the numbers that are given in the problem, but in terms of variables. Then you'll have a set of equations. You use algebra to derive from those equations an expression for the unknown. In this problem, the unknown is the acceleration. Okay, so now you've got an expression for the unknown. That will be a number with a unit. You can calculate the number with a calculator, but you can't calculate the unit with a calculator. To calculate the unit, you have to look at the units in your expression. Combine those units just using algebra, and that will give you automatically the unit for the answer. So that's the four-step process for solving any physics problem, really. And let's apply it to this problem. So first we need a picture. Well, we already have a picture, but let's draw a better picture. So here's the picture. There's the Earth. There's the satellite revolving around the Earth on a circle. The radius of the circle is r, little r. That's given in terms of the radius of the Earth. That's another variable. The satellite is traveling always tangent to the trajectory, which is a circle. So the velocity vector is always tangent to the circle. Probably should have labeled this as v. There's v. Now, as it revolves around the Earth, it's pulled towards the Earth. That's the centripetal acceleration. So there's the picture. Now, what are the equations? Well, one equation is the equation for centripetal acceleration. That's what we're trying to calculate. And the centripetal acceleration is v squared divided by r. That's an equation you have written in your notebook from reading the chapter. Now, the problem doesn't tell you what v is. So you need another equation to determine the value of v. How fast is it moving? Well, it's moving on a circle with a constant speed. So the period of revolution around the circle will be the distance, that's the circumference of the circle, 2 pi r, divided by the speed. If I multiply both sides of the equation by v, speed times time is distance. And distance is 1 circumference, 2 pi r. Now I know what t is. T is 24 hours. So by this equation, I can calculate v. So now I have to do a little bit of algebra. I have to use this equation to determine v, multiply both sides of the equation by v, divide both sides of the equation by t. So v is 2 pi r over t. And now put that into this equation for a, that's the unknown. A will be 1 over r v squared, and v is 2 pi r over t, that quantity squared. So there's the expression for the acceleration. Now you're ready to calculate the answer. The answer will be a number with a unit. So let's see how we would get the answer. We know r is 6.63 times the radius of the Earth. The radius of the Earth is 6.37 times 10 to the 6th. So that's roughly 4 times 10 to the 7th meters. I'll just do this approximately here in the Zoom meeting, but when you're at home, you just do it with your calculator. Get this more accurately. But we can see it's about 36 times 10 to the 6, more closer to 40 times 10 to the 6, 4 times 10 to the 7. That's the number. Now, what about the unit? Well, the only unit here is meters, so that'll be the unit in meters. What about t? Well, t is 24 hours, because this is geosynchronous. It's revolving around the Earth once each day. So that's 24 hours. You can convert from hours to seconds. That'll turn out to be about 9 times 10 to the 4th seconds. Obviously, you have to have everything in standard units, so I'll get A in standard units. And you put this in your calculator, well, okay, you get it more accurately, but roughly 0.2 is the number. Now, what's the unit? Well, we have here meters squared from the numerator, meters in the denominator, so that'll cancel 1 power of meters, and seconds squared in the denominator. So I'll have meters divided by seconds squared. Of course, that's the appropriate unit because it's an acceleration. So that's the standard unit of acceleration. But you don't have to remember what's the standard unit for acceleration. If you do the calculation, including the units, the calculation will tell you the unit. Meters per second squared. So even though this satellite is far away from the Earth, 6 times the radius of the Earth, gravity is not zero. It's not weightless up there. It doesn't have an acceleration of 9.81 meters per second squared, as it would have if it were on the surface of the Earth. It has a much smaller acceleration, but it's not zero. It's 0.2 meters per second squared. And that's the answer you put in the box here. Anybody want to ask a question about this? So let's start by drawing the picture. Here's the picture. We have your initial point. You walk a distance d1 to the east. Then you walk a distance d2 to the southwest. So imagine this is a map, north, south, east, west. Your first displacement is distance d1 in the direction of east. Your second displacement is d2 in the direction of southwest. A d1 and d2 are given someplace. d1 is 1.2 kilometers, d2 is 0.9 kilometers. This vector d1, it's a displacement vector, is x1 I hat plus y1 j hat, where I hat and j hat are the unit vectors in the x and y direction, where I'm calling the x direction east and the y direction is north. So d1 is x1 I hat plus y1 d hat, x1 I hat plus y1 j hat. But d1 only goes to the east. So y1 is 0. x1 is the distance d1, which is the length of the vector, about 1.2 kilometers. Now, what about d2? Well, here's d2. It's a coordinate x2 I hat plus y2 j hat. Now, the direction is southwest. So x2 will be negative because it's south, and y2 will be negative because it's west. And they'll be equal because it's directly southwest. It's at a 45-degree angle. So it has two equal components, both negative. And the length of d2 is the distance that you walked here, 900 meters. So if you know your trigonometry, x2 will be 900 times the, I guess, the cosine of 45 degrees. That'll be 900 over the square root of 2. y2 will be 900 times the sine of 45 degrees. Well, the sine of 45 degrees is also 1 over the square root of 2. So you use trigonometry to figure out x2 and y2, but they're both negative. All right, so step 1 is to draw the picture. Step 2 is to write some equations. Here's an equation you'll need. You have to calculate the distance. So the distance is the distance between this initial point and this final point. So that's where you stopped. So this is the distance that you're calculating for the answer to the first part. Hope you're taking notes. Well, this starts at 0, 0. It goes to x1, y1, that's x1, 0. Then it goes to x2, y2. No, it goes by an additional displacement of x2, y2. So the x component of this point is x1 plus x2. You walked x1 to the east, and then x2 to the east. But since x2 is negative, that means to the west. So the total eastward direction is x1 plus x2. Total northward direction is y1 plus y2. y1 is actually 0, y2 is actually negative. But the total displacement is x1 plus x2 in one dimension, y1 plus y2 in the other dimension. And the length of that displacement by the Pythagorean theorem is the square root of the x component squared plus the y component squared. So this is the net displacement. You started here, you ended up here. That's the net displacement. It's x1 plus x2, y1 plus y2. And the length of the vector is the square root of delta x squared plus delta y squared. X1 was 1242 meters, y1 was 0. X2 was negative 900 over the square root of 2 meters. Y2 was negative, put a minus sign here, 900 over the square root of 2 meters. You take the sum of the squares, it'll be a number with a unit. And the unit will be meters squared plus meters squared. You add meter squares, but then you take the square root. So the unit will be meters, which is appropriate for a distance. And use your calculator now. So you don't pick up your calculator at the first step of solving the problem. You pick up your calculator at the last step of solving the problem. That'll give you the number. You figured out the unit. That's what you type in here. Now, what about average velocity? Well, the definition of average velocity is delta R over delta T. Average velocity, you should have remembered this from, something's going wrong here. Average velocity is displacement over time. So the x displacement is delta x. The y displacement is delta y. This is delta x. This is delta y. The components are I and j, east and north. And divided by a time, well, that's the time that you were walking, 21 minutes. So that's given. So that'll be Vx, and that'll be Vy. And that's what you put in these two boxes. Okay, any questions? You see how the picture is important? You could just do this by, I mean, all you really have to do is do these calculations. But if you don't have the picture, it'll be a little bit harder to figure out what goes in the calculation. Whereas if you have the picture, that's pretty obvious. And that's why you draw a picture. So here's another problem. This is again involving circular motion. It's a loop-de-loop roller coaster. So a car comes down the roller coaster, it comes to the bottom, then it goes into a loop-de-loop. So it goes around a circle like this. It was coming down this way. It was coming down this way, picking up a lot of speed. And then it goes up this way. Oops. And then it goes up this way, losing speed as it goes up. But if it's got enough speed, it'll be able to go over the top and go clear around the circle. Now, you don't want it to fall off. You want the car to remain in contact with the tracks. It has to be going fast enough that it won't fall off the track. So, you need to know a condition so that it won't fall off the track. The speed has to be fast enough. Now, the statement of the problem tells you the condition. The minimum centripetal acceleration at the top of the loop is g, the acceleration due to gravity. In other words, it has to be going so fast that the acceleration of gravity is larger. No, so that the acceleration is larger than the acceleration due to gravity. Then, in addition to the gravitational force pulling it down, the force of the track must also be pushing it down. That means it's in contact with the track. That's what you want. You want it to be in contact with the track. So its acceleration downward will in fact be greater than the acceleration due to its weight only, because it's pushed down by the track. It's in contact with the track. We didn't when we drew the picture, we didn't draw a very good picture. When we draw the picture, we should show the radius. We have the velocity v up here. That's what we're trying to calculate. So the unknown is v. How fast does it have to be going? If it's going faster than that, that's okay. That's the minimum speed. So there's the picture. What are the equations? Well, it involves centripetal acceleration. So the main equation is going to be the equation for centripetal acceleration. The centripetal acceleration is v squared divided by r. That's one of the equations you've written down in your notebook from reading the chapter. And the statement of the problem actually tells you, we'll come back and explain this in the next chapter because it has to do with the force. But anyway, the statement of the problem explains to you or tells you the centripetal acceleration has to be greater than g. So v squared over r has to be greater than g. G is the acceleration due to gravity, 9.81 meters per second squared. Now, r is given in the problem. So if I look at this inequality, I know r, I know g. So I know v. V is the square root of r times g. And this is v squared has to be greater than that v. So what's the minimum value of v? Well, v min will be the square root rg. Now, again, that's going to be a number with a unit. You can calculate the number with your calculator, but you can't calculate the unit with your calculator. You have to look at the units that you're using. R is meters. G is meters per second squared. So RG is meters squared in the numerator, second squared in the denominator. Then you take a square root. So the answer will be, the unit will be meters per second, which you could sort of guess because it's a speed. But this just shows how the units combine to give you speed. And now we have the square root of r, let's say 8.5. G is about 10. It's approximately the square root of 85. So it's about 9, a little more than 9. meters per second. And that's what you put in here. So you see, you analyze the problem before you pick up your calculator. Here's another problem. Oops, this is also a circular motion. I should have put a problem in here involving projectile motion. But here's another problem with circular motion. The moon orbits the Earth in about 27.3 days. The orbital radius is about 384,000 kilometers. What's the centripetal acceleration? Well, that's a lot like the problem we did a minute ago. So that's pretty easy. We draw the picture. Here's the picture. Here's the Earth. Here's the moon. Here's the distance from the Earth to the moon. There's a certain speed. The moon travels around the Earth once every 27.3 days. So R is given 3.84 times 10 to the 8th meters. T is 27.3 days. Now, of course, you're going to want to convert that into seconds. When you do any of these calculations, you should put everything in standard units. The standard unit of time would not be days, although that's the information you're given. But you would convert this into seconds. And then V is 2 pi r divided by T, and A is V squared over R. So, you calculate V and then you calculate A. So you write down in your notebook, what's V? V is, see if I can do this a little better. V is 2 pi r divided by T. Converted into meters per second. And then A is V squared divided by R. So these are equations you have in your notebook. You just calculate this V, calculate this A, and then that's what you put in here. Again, it'll have a unit. V is meters per second. V squared is meters squared per second squared divided by V will be meters per second squared. So the unit will be meters per second squared. Non-kappa will expect that. And then you use your calculator to calculate the number of V squared over R. There's a part B, which is to calculate this quantity. The acceleration due to gravity on the surface of the Earth times the radius of the Earth squared. You know that. You can look it up in the book, or you can do a Google search for the radius of the Earth. It's about 6 million meters. Divided by R squared. Here's the R squared. And lo and behold, you get the same number. So this is one of the ways in which Newton developed his theory of gravity. He said, the acceleration due to gravity decreases as 1 over the distance squared. And that leads to the fact that the force of gravity decreases as 1 over the distance squared, which is an essential part of Newton's theory of gravity. So this was a famous calculation done by Isaac Newton. All right, any questions? So let me just repeat what I said at the beginning. We're finishing the third week of the semester. The fourth week of the semester will be the next chapter. And then we have the exam. So there's an exam coming up. You should keep that in mind. You're going to need a page of equations to refer to during the exam. Chapter 4, that's next week, is probably the most difficult chapter in the book. So be sure you leave yourself plenty of time to work on the problems in chapter 4 and to write out your equation sheet to use during the exam. But chapter 4, I mean, chapters 2 and 3 are a little easier. Chapters 2 and 3 are really just math. But chapter 4, we introduce the concept of force. And that's not just math, that's physics. So things become more difficult when you involve new concepts like force. I didn't go over any examples of projectiles. There's a section on projectile motion, and there are a lot of problems. So you get plenty of practice solving problems of projectile motion. One thing to notice is there's a summary, which is table, if I'm remembering correctly, it's table 3.1. Summarizes the equations for solving projectile motion problems. So in the process of reading chapter 3, you should write down the equations that appear in table 3.1. You'll have all the equations that are necessary to do calculations for projectiles. Okay, so let's see if there are any questions. Well, there's a question on the chat. Can you go over the question that is titled an additional problem? Possibly. Let me start by ending the recording. Okay,